everyone, it's Judy Warner. Welcome back to this week's Ecosystem Podcast. Today I'm joined by Randy White and Stephen Slater of Keysight Technologies. We're going to take a deep dive into memory design and simulation, specifically in DDR5. They're going to give us a sneak peek of an upcoming webinar on September 13 that's going to talk about Pathwave ADS 2023 high-speed digital design and simulation. Even though that's a mouthful, I think you're really going to enjoy this conversation where we talk about the ecosystem that exists around DDR5. We're going to talk about an upcoming update to the JEDEC standards around DDR5. We're going to talk about the importance of guidelines that always changes each time DDR has a new iteration. And we're also going to talk about ways that there's such innovation around the area of pre-layout simulation that results in fewer board spins and a huge savings on costs and time. Make sure you check out the show notes. There's lots of resources for you there from JEDEC, Keysight, and there's also a link to this upcoming webinar where you can take a deeper dive into the subject. I think you're really going to enjoy this conversation. Now let's join Randy White and Stephen Slater of Keysight Technologies. Hi, Randy and Stephen. Thanks so much for joining me today. Before we get started, Randy, let's start with you. Tell us a little bit about your technical area of expertise and what you do for Keysight.
Sure. Yeah, I'm the Keysight Memory Solutions Program Manager, which, in a nutshell, that means I'm responsible for overseeing the development, and I manage the various solutions for validating memory, and also as an added benefit, I have the opportunity to represent Keysight on the JEDEC Standards Committee.
Awesome. Stephen, how about you? Same question.
Yeah, hi. Stephen Slater. I'm a product planning and marketing manager for Pathwave Software Solutions. So basically, Pathwave ADS and all the simulation technologies that are behind it. I have a team of 3 product owners and application engineers, and everything that's responsible for DDR, electromagnetic simulation, high-speed SerDes. That's in our wheelhouse.
Thank you. Well, I'm excited to have this conversation. You both are teaching me, and I'm sort of onboarding this knowledge. So I've really enjoyed getting to know you both in our earlier calls. So Randy, I thought we'd start with you. Today we're going to be talking a little bit about DDR5. Can you believe we're there? And why that technology has persisted as the prevailing technology that we're continuing down the road as opposed to other technologies?
I think that's a good question, and that question is on a lot of people's minds who may be starting out. Like, why are we still continuing with DDR when the 5th generation? What's made this so successful in terms of sticking around? As it might not come as a surprise that there have been other competing memory technologies that have come and gone and have not endured, and they each have their various strengths and maybe disadvantages. But there's a phrase that I tend to hear quite a bit with DDR, especially DDR5 lately, is it's a commodity memory, right? It's commodity in that it tends to be high volume. And that, in essence, is the kind of secret to the success of DDR memory. We're balancing performance, trying to meet the various performance metrics like latency, speed, capacity, which those have their own costs in of themselves. But at the same time, we have constraints on the other side that could limit the performance, like power. And of course, I really think the number one driver that's made DDR persistent is cost. And the price point per gigabit for a given memory device certainly outweighs the equivalent cost performance that you would get from alternative standards. So, as they say, if it's not broke, don't fix it. And DDR is not broken so far.
Yeah, so far. And cost is always a relentless driver, as well as speed and technology and all those things. So that makes a lot of sense to me. Um,
It's not run out of puff yet either. So with the latest developments, keep doubling the data rate and moving things forward. Things are getting more challenging, but then more technology comes in to try to ease those challenges. So there's still bandwidth. We're not at Shannon's limit yet, so we can
hmm.
keep pushing ahead and evolve the current standard rather than be a huge discontinuity to change to something completely different. And cover as many use cases as DDR can, because DDR is so versatile.
Yeah, and the bandwidth thing is a big deal, obviously, is like, and it's crazy to me. Like, I remember DDR2 and 3, and it just seems like we blinked, and we're at 5, and now people are, playing around talking about 6 a little bit. And it always amazes me how we keep doubling data rate and just doing this. It just always blows my mind, but it doesn't seem like you said to run out of steam yet. Randy, you mentioned briefly your role on the validation subcommittee at JEDEG. Can you talk about, like, you're obviously an internal employee of Keysight. Why why did you choose to do that? And it seems like something Keysight's decided it's worth investing you as a resource. Um, what was the thoughts behind that? And can you tell us a little bit about what that's like, and what the focus of that validation subcommittee is?
Yeah, you're right. Earlier I mentioned, my primary focus at Keysight here is to help drive the development of our solutions that our customers need to sign off on their next gen memory designs. But also part of that is sort of a forward looking role in the industry, and that's
Hmm.
within JEDEC. So JEDEC is the centralized organization that manages and defines the specifications or the standards that go into today's microelectronics, and memory is a big part of that. And like I said before, it's a commodity. So if we need to implement a commodity memory that is consistent in its performance, it's financially viable, that's where JEDEC comes into play, and they do a great job there. So my role, why is Keysight saying, okay, you
Yeah.
have an internal focus of working with the teams to develop your solutions, but at the same time, we also want somebody to participate and contribute and represent the interests of the test and measurement industry within this organization. It's
Mm-hmm.
important because if you can't test it, you can't fix problems.
Right.
There's this concept of design for test, meaning
Mm-hmm.
having a strategy that incorporates test and validation up front in your product development lifecycle. Keysight feels it's very important to make sure we represent the interest of the industry from the perspective of test and measurement, because that's a critical function in the product development lifecycle.
I might
That's
put you
very
on this.
true.
Go
Very true as
ahead.
well for this change from DDR4 to DDR5, because you probably get into it a little bit later, Randy. But one of the key things was the test measurement point where you're making the measurements has moved inside the die now, and without the test and measurement, insights, trying to help out the specification, it'd be rather difficult to come up with something that would actually have a full compliance test for DDR5 without that input and insight.
Yeah, for years and years, memory, especially DDR, has been about managing setup and hold time. Right, it's a clocked it's a source synchronous bus. So we send a clock along with the data, and we have to make sure we meet those setup and hold timings.
Mm.
And designers for years have padded or added a guard band. And in a way, the system has been over-designed. So they're giving up margin.
Yes.
They're over-designing their
Yes.
for what's required. And then now the margins are getting so tight with the higher speeds, it's just nearly impossible to scale the setup and hold requirements and limits that they would need to meet the higher speeds. So we have to think differently about this. And to what Stephen said earlier, it's a great point. Part of thinking differently is thinking more about the performance of the receiver, which incorporates a lot more functionality like equalization. And how do you test that? It's never been done before, at least in memory. So it makes for a fun and interesting engagement within JEDEC.
Well, one thing I have appreciated about getting to know some of the internal experts and stakeholders like yourselves regarding Keysight is kind of this, looking at like a design for test and then the test, right? Because internally because you make your own instruments, right? You face this as a company and also your customer base. And it's just a unique thing to have the software and the hardware so coupled and sort of have, like I said, the ecosystem. Obviously, that's why I named the podcast there. So, Randy, you'd mentioned to me, first of all, I got to ask this question that I haven't asked before. And sorry if I'm putting you on the spot. What does the acronym JEDEC stand for?
Yeah, it's a mouthful. Joint Electron Device Engineering Council, and that sounds sort of ambiguous or maybe not so clear, but it's essentially a standards organization that defines microelectronics, either at the package level, the interface level, mechanical. There's high band gap power electronic semiconductors. There's small signal DRAM, DDR device definitions, and anything in between. So microelectronics is what JEDEC focuses on.
Interesting. Well, thanks for unpacking that. I never, I've known about JEDEC for years, but I never thought to ask anyone what that acronym stands for. So what I was starting to unpack here, and I'd like to hear from you, Randy, on this is, I think now more than ever, for the reasons that you've both mentioned, that we have to, even if you're not a systems engineer, you need to start to think like one and at least understand what your upstream and downstream stakeholders are up to so you don't hit your head, right? Or trip at some point because of a blind spot. And you have loosely described to me that there's an ecosystem in which when it comes to memory, you've touched on it. You've both touched on it, right? But can you sort of unpack what that ecosystem looks like so that people are listening can understand sort of from a systems-based approach? What is that ecosystem that creates that visibility?
I like that. I like that question. It's fascinating because I think about it a lot. Being from Keysight, we serve and support a number of customer use cases and kind of stages of a product life cycle, be it semiconductor, silicon, or final system production test. But I think in order to understand the ecosystem, let's back up a bit and let's take a look at the organization of JEDEC itself, which will then lead into further explaining the ecosystem, because they're mirrored in some degrees, in some respect. So JEDEC, as I mentioned, comprises various organizations that have their interests represented through different working groups. And these working groups are structured by committees and subcommittees. And then within these subcommittees, you have task groups. So at the lowest level, the task groups meet on a weekly basis and discuss different topics. As we move to DDR6, there's a task group that's organized around what is the interface for DDR6 look like? What are the minimum requirements? What are the nice to have and the optional features that need to be incorporated? And then as those task groups work together and come to a consensus on these are the requirements, these are the specifications that we agree on, right? Because there are multiple companies that are actually competitors in the market, but in order to work together and standardize, come together on a standard, they work together as many other standard bodies do.
Sure.
So this bubbles up to a subcommittee, and there's a voting process that happens on a quarterly basis, and then that in turn goes up to the committee level, and then finally it goes up to the JEDEC board of directors, and they have the final vote and approval for which this feature, and maybe it's a set of features to make it more efficient, all these features then get rolled into a future version of the specification. So DDR5, for example, it was introduced in July 2020. So we're about 2 years into the life of DDR5. In general, it takes a specification about 5 years in JEDEC, from back of the napkin numbers and specs to it's actually published on jedec.org. And so there's a lot of back and forth voting. And like I said, board of directors will take that draft spec, whatever it may be, and then approve or reject. Now, going back to the ecosystem question, task group subcommittees, there are different task groups and committees for different parts of a memory design. I mean, that's one way to simplify it. You have the interface itself, right? You have the pin, the signal that's coming out of the pin, that's the interface. Then you have the device, right? The DRAM, or it could be SRAM, or it could be any other memory type. And then from there, if you go up a level, you have the system, which JEDEC, it turns out, currently does not define the system specifications. So we more or less stop at the device level. However, as a courtesy or way to simplify the memory module adoption and design, JEDEC does publish the specifications for the layout and the bill of materials and the schematic for the memory modules that you would plug into a system. So that's the highest level that you'll see at JEDEC. Now let's translate this to the industry. Within a system, you have different components. The DRAM is sort of the central part, right? That's the part that's storing the data from the memory controller. And so you have the main, there's many DRAM companies, but there's basically 3: Samsung, SK Hynix, and Micron. And then in terms of more importance for a memory design, we see a lot more emphasis and capabilities in some of these peripheral support components. So SPD, serial presence detect, it's like an EEPROM that stores the memory module contents. RCD, register clock driver, it's a buffer and a clock buffer and a command address buffer. So a lot of these components are very important. And for DDR5 to get to the higher speeds, some of the companies like RCD, Rambus, Renesas, Montage, those are the names that you'll hear. Those get implemented into a system. And so I suspect a lot of the audience listening to this podcast today is probably more on the latter part of the supply chain, if you will, for a system.
Right.
So it's important. It is important to understand how JEDEC works, to know your suppliers and what they think about and how they validate. So that way, when you integrate their components, you have a better feel of the big picture.
And it sounds like a great place to tap into, say, if you're going to do layout and all of that you can, connect all the dots, so to speak, right? And have those guidelines. A question I want to ask you, Stephen. So recently, I interviewed Ben Dannon, who is from Northrop Grumman, and he mentioned that he's done some work with you. But an interesting thing, and again, this is part of my own learning curve, is he was saying that memory design, that engineers on a whole see it as difficult, and sometimes people avoid it because they don't want to.
Mhm.
And Ben was talking about sort of his own journey of like he loves it now, but he had to go through a learning curve. Can you tell me a little bit about why it's so hard and like people like Ben, what is that evolution look like to onboard that kind of knowledge and capability?
Yeah. Yeah, some of our customers actually will have someone in their team that kind of specializes in memory, and all the memory
Mhm.
designs go to that one person. But that's not true of all organizations. There's plenty of organizations where there's a product and there's a single hardware engineer responsible for the entirety of that project, and they have to do everything: the high speed SerDes signals, the high speed memory. It's all part of what they need to do. Um, Ben is a very impressive engineer, and I think the thing that comes across very clearly is that he's got such a curiosity and enthusiasm for what he
Mhm.
for what he does. So
Yeah.
when he chose to jump into memory, really and truly, it was just work that was outside of his kind of day to day job, and he wanted to write a like design comp paper and get into it. Um, it's actually not as hard. It is daunting from the outside, and I think the thing that is daunting about it
Yeah.
is there's so many signals, so many signal names, so many types of measurements, so many rules around how this technology should work. But probably my own experience, how to get into it. I found very useful the like AMD Xilinx signal integrity user guides. They kind of give you
Okay.
signal integrity guidelines for impedances and how long the traces should be, what the termination settings should be at the end of the line. It kind of goes through some of the choices that you have. And then you've also got like Intel's platform design guide, which is, there's a lot to read, but you scan it first and just try to let it sink in. But then try and take that knowledge and move it through into your very first kind of mental model of how this should work. And the mental model would be trying to build it in a simulation environment. So you build it up as transmitters and receivers and transmission line sections between. To start with, you can leave the vias out of it and just have pure transmission lines and simulate that. Look at the eye diagrams, make some of the measurements, and then you're
Mm.
slowly and slowly building on additional layers of knowledge. And adding in more complexity. Um, so like there's lots of features in DDR, even things like they call like a data bus inversion. Okay, so at first you might be like, well, what is that? Do I need to worry about it? But you don't need to worry about it to start with. You layer that in later on, and so you build up this mental model of how it's working. And we tend to call that like pre-layout design. And
Mm.
then from
Okay.
there, you've got a good confidence that the design should work. Then you can go and start to actually lay out the board, the PCB. Um, and then the final kind of thing is that once the PCB is actually laid out in like an enterprise, layout tool, you can never kind of fit everything in exactly how you wanted to. So your ideal structure never ends up being like that once it's actually
Yeah.
on the board. So
Yeah.
what you do is you
True.
bring that one back then into the simulation tool, and you do an electromagnetic extraction. So basically, you're trying to take all these signals as they've been routed, and we're going to extract an S parameter model from them.
Mhm.
And then you drop that S parameter model back straight into your schematic. So where you had all those transmission lines before, you remove those and you drop in this S parameter model. And you rerun the same simulation and you verify that it's still going to work. See, do I still have open eyes or have they, now closed? Look at the timing between particular signals, make sure that they are within spec. Um, and that's how you kind of build up confidence that your design is going to work. And then the final thing could be moving into compliance with virtual waveforms. But I think maybe we might discuss that. I'll leave Randy to kind of introduce the concept of compliance test first, and maybe we can talk
Yeah.
about that from the simulation perspective a little later.
Yeah. Well, thank you. That was a really good explanation. And even for me as a civilian, that sounds like a good way to break it down and make it more relatable, that you can do it in sort of a virtual way, before you put skin and money in the game. Um,
Absolutely.
so I wanted to ask you a bit more, Randy, about the ecosystem and the impact, say, of going. You mentioned that it takes almost 5 years from napkin to having a standard. So I'm kind of interested in what happened between DDR4 and DDR5, how that impacted the ecosystem, and sort of where are you in terms of when the DDR5 standards will be out, and how it's, obviously every time we make a jump like that, it affects designers, right, at every level. So what is the impact of all this sort of? So if you could unpack that a little bit, that'd be interesting, I think.
Yeah, it is really interesting to look at DDR4 versus DDR5, and what are people getting themselves into when they advance to the next
Right.
generation. I guess I've got good news and bad news.
Yeah.
I always like to start
Always.
with I always like to start with the bad news first, right? It softens the good news makes up. But the bad news is yeah, this is much more complex. This is a significant architectural change, and what I mean by that is DDR4 had some very basic equalization and compensation functions built in. They were optional, and so for more extreme cases, you would see maybe a couple of taps of DFE, a CTLE or FFE on the transmitter side, but it wasn't specified, and yeah, it was a bit of the Wild West. As needed, it would be implemented. Now, fast forward to DDR5 with the channels are more or less the same, right? We're not going to go longer, we're not going to go shorter. You have to route from the processor or memory controller to your slot up into the module. The channels are nearly the same, right? They're typically a centimeter or so, but the speeds have doubled, right? And we still have, like Stephen pointed out earlier, we have decisions to make in terms of how many slots do we want? 1 DIMM per slot, 2 DIMM per slot. Hey, the more DIMMs we have, the more memory we can address and our capacity increases. That's great, right? We can run more virtual machines per core. That's great, but the price is paid in signal integrity and load. Can the memory controller handle that much load? And so there's been some provisions along the way that have made DDR5 an evolutionary change. So from the power side, right, we've switched to this idea of a PMIC, power module IC, whereas before the voltage regulation was managed by the server or the host, and then the respective supplies were kind of funneled into the memory module. And that made it hard because any given system, whether it's a small capacity or large scale, cloud server, you always had to design to the worst case power budget, and it just wasn't cost effective. So now the PMIC allows the designer more flexibility because the voltage regulation is handled at the source, at the memory module. And that decouples the ground references. So now you've got, a bit of a benefit in terms of signal and power integrity noise, and you got the cost advantage. So little things like that have added up to make DDR5 better for the end user, but it makes the design process more complex. So that's the bad news. The good news is like I said, there's a lot of benefits in performance. The back of the napkin part of the standards development process that I mentioned, at some point along the way, the JEDEC team, DDR5 teams did a lot of simulations and said, we cannot make this work at the higher speeds without equalization. I'm sorry, but we are going to have to use DFE. So a 4-tap DFE receive equalizer has been implemented. And this is really, I don't want to say the secret sauce, but it's really been the pivotal element that makes this whole work. The first round of DDR5 designs, what I would call first generation, up to 3200 up to 4800 speeds, I wouldn't say the eye is closed in general. In some cases it is, but the industry now is moving forward to higher speeds, up to 5200, 56, even 6400. And especially with a 2 DIMM per channel configuration, the eye is going to be closed. And so I would say if you're not familiar with equalization and the concept of DFE, it's probably something you want to learn about and educate yourself so you can be more comfortable when you start incorporating that feature into your design.
I really know nothing about equalization and DFE, and I'm wondering if the people who are listening do. Can you just give us a brief overview of what that means to the design? What is that? I really don't know. So
yeah. So a lot of other equalization techniques rely on applying some type of gain, right? We're going to apply gain at this frequency point, and we're going to boost the edge, like de-emphasis or pre-emphasis. So that's often employed for the transmitter. So it's a pre-distortion technique.
I see.
DFE is very common and mostly used for the receiver, in that there's a lot of distortion on the signal as the receiver sees it. So to help the receiver better detect the signal, this is a decision feedback equalizer. And so the way that when the signal comes into the receiver, it goes through what's called a slicer. And a slicer, like the name implies, has a threshold. If it's above the threshold, it's latched as a certain logical value or state. And if it's below the reference threshold, it's a low state or zero. Decision feedback equalizer allows us to add certain weights to that threshold. So as we detect certain bit states that are coming in, based on the history, right? If we have a long string of ones, right, and then all of a sudden we transition to a 0, you can better believe that 0 will be a lot smaller than had we transitioned from a 0-1-0 sequence.
Right.
So
right.
DFE allows us to dynamically and on the fly change the receiver threshold to make the job of detecting the signal easier.
Interesting. That's way out of my knowledge, but I tracked it pretty well. So thank you for explaining that, not only for me, but for our listeners.
Another way to think about it as well, and maybe this might be useful for those who are watching the podcast visually and not listening to it, is maybe if we flash up an image of what a single bit, like a pulse response, looks like before and after decision feedback equalization. And what that picture is going to show is that the pulse that you sent was like a beautifully undistorted, 0-1-0. But then once it goes through the channel, a lot of the energy from that pulse gets spread over future bits, basically. So it gets spread and gets the receiver at a later time.
Yeah,
so
love to see that image,
yeah.
by the way.
Yeah, and then after equalization, after the DFE, you'll see that all of that energy that happened in those, future bits, the bits that to come yet, they get removed away. They get deleted or compensated for. And so I think that would be it's a nice way to try and understand exactly what the outcome of DFE is and why it would make the signal better.
Okay, make sure you send that to me.
I will do.
I'll get back to you
I
on
thought
that
that'd be
one.
a good one, a good one to
Yeah,
throw in.
no,
Yeah,
a
we've
picture's
got
worth
an
a
image for
thousand
that.
words, right? Okay, good.
Judy,
Go ahead.
sorry, one more thing. Sorry, I don't mean to scare everybody, but we want to educate the audience about
Yes.
what's coming. So it's one thing to validate and verify DFE in a DDR5 device standalone, which all the DRAM companies do.
Mm-hmm.
But once that device shows up on a system, in essence, you're kind of throwing it over the wall. How does a system designer verify or validate the DFE performance within the system itself? Because now you've got the
Yeah.
channel. That specific channel was not tested at at Micron or Samsung or Hynix. I mean, they have their own test channels and they do characterization. But now you have a system designer that has their specific design.
Yeah.
How do you know it works, right? And this is where the beauty of the memory controller training sequence. And I think this is also, this is complex, right? There's no spec on it, and it's very customized for a given channel. It's the BIOS. The BIOS is the software that's under the hood that will go out and do some right leveling sequences and other forms of training to optimize the delays, the termination, right? There's different terminations depending upon if it's a single rank. A rank is a group of devices, or if it's a multi-rank, you can talk to multiple devices at the same time. So I would emphasize that the training is really, really important for DDR5. I mean, it's great we've got equalization, but you have to make it work in the context of your design.
Yeah.
And if you don't have the training right, I mean, the thing, you won't even be able to boot.
Right. So what's the best way to onboard that? Like that blind spot. What's the best way to do that?
Yeah, that's a good question. I think
Sometimes I
Stephen,
feel like I just ask almost near impossible questions or, yeah, well, anyway. So sorry if I'm
no,
pulling you
that's
into the weeds deeper.
yeah. Stephen alluded to this earlier. So again, the good news is we're not throwing the system designers out in the cold, right, to fend
Yes.
for themselves. Stephen mentioned this concept of a design guide, and the design guide says that if you follow this stack up, this
Mm-hmm.
layout, this
Yes.
structure for your channel, you should be good to go. But we all know that there's not a one size fits all. So there's variability and there's some tolerances that are given for people to customize to their needs. And that holds true for the BIOS. So there's a
I
memory
see.
reference code in the same way that the design guide says, here's the recipe to create the
Yes.
hardware. There's a similar guide for the software where one can then, if you follow this memory reference code, and here are the parameters that you can tweak, you can train this way, you can optimize for the different topologies that you need to support, you should have a high chance of success. So that tool is there in the industry, and without it, it's very difficult to, you don't want to
Yeah.
reinvent the wheel.
Well, I'm glad it's even there. Sometimes, like in the podcast with Ben, I asked him a question. He's like, yeah, that's a good question.
Yeah.
So it's really good to hear from you that there's very specific things. Well, you're sort of helping me to segue into a question I have if I was listening or watching this is, so what specifically you're talking about the design guidelines, right? And what are some other ways that you can tap into really meaningful resources, right? Um, like this specifically. Yeah, Stephen mentioned earlier about AMD Xilinx and Intel. That's a really good piece. And Stephen, if you wouldn't mind sending me those links, I'll put those below in the show notes for our listeners.
Absolutely.
Um, what other well, let me back up a bit. So we need resources, but you've mentioned to me in an early conversation that what's really needed is kind of this comprehensive um, design and test strategy, right? And so how do design or systems engineers, like, what are good practical resources that they can go to tap into some of this knowledge?
Yeah, so I threw out the phrase design for test, and that's important.
Yes.
But what you said and what I also am of the same opinion is it's kind of taking that to the next level, and that's a design and test workflow. And so, what does that look like?
Mm,
That's a must-have strategy going forward.
mm,
Recently, I was talking to a validation engineer at a large a memory company, and
mm-hmm,
I said, so your job is to kind of receive the hardware, the prototype. You have a power on, you turn it on for the first time, and you check the vital signs and you see if it's working, and then eventually you generate a report, pass fail. Do you know how do you know what to expect in terms of the results? He says, I don't know. And that at that moment when I heard him say, I don't know what to expect in terms of the results, that really scared me. I know it sounds cheesy, but I just thought you really should, whenever you start a project, you should know the outcome, what to expect. And so that's where I realized linking the design phase in simulation with the validation phase in the lab with hardware, that is such an underserved need. It's
mm-hmm.
something that has evolved, it's been there, and now it's so important.
Right. So to that point, I know that, with an upcoming webinar you're doing about some new features in ADS coming out, right? There's some of those things, right, available from Keysight. And I'd like to hear about what specifically those are. But, I did a podcast not long ago with Matt Ozales, who's on your team, and he was
Mhm.
talking about this overall move towards this shift left,
Mhm.
right? Where, like you said, design with test, and reminds me of that old, what was his name? Wayne Dyer, that said, begin with the end in mind, right?
Hmm.
But validation in the front side through, I mean, not validation, simulation. When we were talking earlier, and we'll unpack this a little bit about validating up front, which was Stephen was talking about earlier, and having that ability to sort of do that virtually before you're 3 spins in, right?
Yeah.
It's not shoot in the dark, get a proto, da da da, and then throw it in the trash, start over. Um, so I know you have some apps through you, and um, for our audience, they are going to host a webinar that's going to talk about some of this virtual simulation. What they're talking about, which is relatable to me, is like what'd you say, Stephen? Like a simulation wizard, that can kind of
Yes.
walk you through that in the
Mhm.
tool. But that's on September 13th, and I'll put the registration information in the notes below, but that's coming. But as we, sort of get closer, I want to give our audience some real critical takeaways. So, what are some of those apps? Um, and then, if you could um, talk about what you're going to discuss in that webinar and
Yeah.
what solutions Keysight's coming up to as they face down some of these challenges.
Yeah, certainly. Thank you. So, let me take it all the way back to one of the very first things you said about, shift left. That's one, just one of several, let's say, interconnected big themes out there. So, um, agile design methodologies, which usually apply to software, but it's being applied to hardware design now as well. Shift left, that's another kind of a big theme that's out there, and and digital twin. These are all like big buzzwords. But we try to break it down. What is it really? Um, well, it's moving hardware design from the traditional a V kind of like a waterfall model where we do a bunch of design, specs come down, do the design, get down, prototype, and then go and validate and test, etc. Um, and trying to bring um, iterations of the design earlier. So being able to do shifting left, it means hey, if I'm going to eventually sign off a design with a compliance test on the bench with hardware, why don't I bring those tests and measurements earlier? Why don't I bring them into the simulation part of it so that I can find issues earlier, and that should save me a bunch of time because it's very costly to fix something that's discovered way too late. And put things in perspective, because this is all just high level, but um, in the webinar that we provide, we're going to be talking to Seiko, one of our great customers from Italy. They work on some really cool like embedded system design. It's kind of like high performance computing for industrial automation or like computing at the edge. And one of their challenges is they have to shrink everything down into a small real estate. So they have to do some stuff that goes outside of like Intel's platform design guidelines. Their via structures are really cool because they have to use like laser vias to try and fit everything in and get all the signals into where they need to. So for them, they got a complex design. They can't really stick to the Intel's design guidelines. They have to simulate and have good confidence so they can predict how it's going to work. And before they did any simulation at all, it used to take them about six design spins, like six PCBs, before they eventually get to the production build. Now the third iteration is the one that goes to production. So they have a first prototype, they make some changes, second prototype comes, some final changes, and then that third one's ready for production. So they save themselves a bunch of time, but what they're doing is they're shifting the effort and focus into doing more simulation up front. But at least in that method, they get to predict their design cycles. They don't have any last minute surprises, and they have great confidence that it's good.
Yeah. Which is what Randy's mentioning, right? Is like, what do you mean you don't know what to expect, right? And so that gives you, and I have more experience on the board level side of hardware, and that is one. I mean, there's so many sides of that when they get to that point that is costly, cost wise, time wise, and time to market. I mean, it costs them at every level it could possibly cost them. And so, I mean, going from 6 to 3 spins can't be overestimated. That's massive improvement.
Yeah, but one thing I would say about it too is, I think naysayers would look at it and say, yeah, but it's really quick for me to just push out another build of the board. So, how much time am I going to spend in simulation versus how quickly I can get another board out there? I think that is would have been true, except that more recently we've been delivering like application focused like these simulation wizards or templates. So our product in ADS called Memory Designer for all of those next generation memories. So if it's like DDR4, DDR5, or even like HBM3, all of these next generation memory technologies, we've got we start to treat it at a level of abstraction. So you've got a memory controller where you can specify as many signal nets as you want, and it identifies them correctly. And then you wire a single bus wire from it to the PCB model, and then out to the receivers, and then a memory probe. And what that memory probe does is it can access the waveforms at any location throughout the schematic. So if I want to do analysis of the eye diagrams anywhere on the board, it's really simple. You just do it as like a group. All these signals are alike. I want to set up the measurement and go. And then the final aspect would be the compliance test. And that's something that, Randy touched on, but I think it makes sense to bring it back, close now, which is, yeah, this is exactly the same compliance application, making the test specifications as per JEDEC, and it's making the measurements on simulated waveforms, virtual waveforms, exactly as you would on the bench with real hardware measuring, real waveforms. So you've got this one thing, this one kind of the source of truth, maybe one single source of truth that's saying this is the measurement as I made it, and then I'm comparing the same numbers to what we see on the bench. And if there's problems, if there's something that doesn't line up, then you should be able to pinpoint, or at least it highlights that there's a gap between what we eventually built and what was modeled. So maybe the models need to be updated, or maybe something was very different in the layout that shouldn't have been
I'll
there.
link. I'm sorry, Randy. Go ahead, and then I want to tag onto that thought.
Stephen hit a resonant chord, a resonant frequency in my head here with that last statement. We're talking about. We originally started talking about results prediction, pre-layout, prefab. I mean, that's nice, and yeah, I think that definitely is a time-saving feature. But I can't stress enough that what Stephen said, the last part, was about model correlation. So results prediction is a basic time savings, but how do you know if you just get results faster, how do you know the results are accurate too? So I think another element of this is refining your models. And so now you can accelerate that process because it's a closed loop process, simulate, build, fab, test, resimulate, and you're kind of doing this in the loop. But now we're accelerating in that loop because we're kind of, taking one or two steps ahead in advance. And then we can go back. Hey, what if I swap out a different package type? What if I switch from a single rank to dual rank? So you're running all these what if scenarios that would be hard to build or, prohibitively expensive. But at the same time, you're also refining your models. And who doesn't want to have accurate models? I mean, that's a very important.
And I think, again, most of my knowledge is on the board level type. And what made me really interested in having this conversation with you was because, again, in the podcast with Ben Dannon, he was saying that he got a model. I don't remember who it was from. Got a model. He was running the simulations, and he says it was just off a little. But he wasn't quite sure, and he has a process, and he hadn't yet put in the board effects, and so he called up Steve Sandler, right? And both of them have told me in different ways that, Steve has said to me many times, like, in the olden days, the board effects just pretty much didn't matter, right? And then as we go to higher speeds and frequency, it's like all the problems, there's so many problems are at the board level. And so then Ben was able to figure out, Steve said, it's probably the board effects, right? And so then he added in the board effects, and it was perfect. But the model from the chip manufacturer wasn't quite accurate because it wasn't allowing, and he wanted to correlate it. Mm-hmm. And it was just that simple, problem solved. And so for him to have that kind of insight, before he was way downstream, I mean, that really spoke to me anyways.
It's funny you mentioned that, Judy. This is a coincidence. I think that project was a paper that I did with Ben for DesignCon. Maybe it was, maybe it wasn't, but
he mentioned that he had done a paper. Well, he had done some with some colleagues, but I know he was doing work with you. It may have been.
Yeah, but and the specifics of that was the model from the supplier said the ODT is this value, right? The ODT is the termination that preserves the signal integrity, but we were measuring something different, and it took time to get the board to set it up. So there was a cost associated with fabbing the board. We didn't fab it, but setting it up there. Had we had a more complete system model that was accurate, that would have saved us probably a few months of effort. But it wasn't until we got to the very end when we made the measurements and we're scratching our head like, why is the signal look like this? Because the ODT in the simulation environment gave us a different view. So we had a disconnect. Boy, I wish I had this linkage a lot sooner.
Right. Yep. 3 months. I'm so sure that is an enormous amount of time in engineering. And so, yeah, I mean, I'm sort of following a rabbit trail because both Steve Sandler, who is, of course, a power integrity specialist, he's saying board effects used to not matter. Now it's always board effects. And without that cohesive kind of systems-wide intelligence, and now you're making tools that can give you those, that's like a sort of a transformational moment, it sounds like to me, in the industry, being able, and they've both Ben Dannon and Steve Sandler said to me, what's great about Keysight is that you get that end-to-end, where you can look at it from a systems-based approach with all the pieces, across. So that's what got me interested in wanting to have this conversation. Then I knew that your webinar has come up. Well, gentlemen, thank you so much for this conversation. About solutions-wise, Stephen, before we go, was there anything you wanted to, at the risk of sounding a little bit like a Keysight fan guy, but that's okay because it is exciting, and I don't want to miss that point. So before we close here, you want to talk a little bit about what specifically those pieces are that enable that end-to-end
yeah, sure.
solution.
So I'll speak about the simulation side, and then maybe Randy would talk about test side. But this upcoming webinar, we're going to be focusing on Pathwave ADS, in particular the memory designer feature. Got a brand new tool in there called the pre-layout builder, and it's kind of like a wizard that helps you to build out what the pre-layout should be. So it makes it nice, and it just accelerates your design cycle basically. We also extended support, so now we have like LPDDR5X and HBM3. We also did all of the GDDR6s and 7s, so that was from prior. But anyway, broad range of support. But then that it's not all just about memory. The rest of the webinar is going to focus on new standards and reference channel support for like PCI Express, Gen 5, Gen 6, USB 4. So a brand new set of features for that. And then also into power integrity. So in power integrity, we've added a brand new analysis type, which is focused on radiated and conducted EMI. And that's an interesting topic in itself. It's a whole other topic and domain. But
yeah, it is.
But in a nutshell, what we're trying to say is that you don't need to be scared of it. A power integrity engineer sets up their simulation, and it's really easy now just to be able to move that into a radiated and conducted EMI test bench, and just get the check in the box and see what might be problematic on the board. And then the last thing rounds off with a look at high performance computing, which is speeding up your simulations with parallel sims and how to do that effectively in the cloud. And then the last one is power electronics. And power electronics is another whole other area where people are looking at how can they develop really high efficiency like low noise power. And nowadays, power electronics has gone into things like gallium nitride, which has trade-offs.
Right.
It's like really high voltage, but you also get really high efficiencies out of it. So yeah, that's in a nutshell what we're going to be talking about. And I don't know, Randy, do you want to maybe talk about any of the solutions?
So on the other side of the world, there in the lab, you'll find the typical workhorse of the high bandwidth oscilloscope. And unlike a lot of other standards that use cabling for signal access, memory tends to lean more towards high bandwidth probing, differential probes to access the signals mid-bus. And new for DDR5 is, we didn't talk about this a whole lot, but to really test the receiver, DFE, there's a receiver test, and this is test you use a bit error rate tester, a BERT, to do that. And then lastly, there's the protocol aspect, which is just looking at the commands going back and forth and refresh management, training sequences, things like that. So we use a logic analyzer for that.
Awesome. Well, please, if you would, be so kind for our listeners to send along some of these resources we've discussed. Randy, we didn't talk about it, but you mentioned, for instance, we've barely scratched the surface here. But we'll put some links in the show notes, not only to the webinar where people can learn more, but also to the Pathwaves resource page where there's lots of good learning. But Randy, you had talked about a really deep dive on the JEDEC side. So if you briefly talk about what that is so our listeners know what the link is, and then we'll make sure to share that as well.
Yeah, just really quick to touch on that. JEDEC does a really good job of industry enablement, and they host various workshops and seminars. In May, they hosted in San Jose, they hosted an all-day everything you want to know about DDR5, how the spec was developed, what are the training sequences, what are the typical use cases, how do you validate, why does DDR5 use DFE, and so much more. But at 8 hours, this is a boot camp style training session from all the industry experts in JEDEC. So all the architects and the principal engineers that sit on JEDEC and drive the development of the standard, they're the ones that hosted this presentation. So JEDEC recorded the presenters and has the audio and slides, of course. So these are available at jedec.org. You can access those there, and I highly recommend as a further step beyond what Stephen mentioned and you mentioned about the webinar. But if you really want to go deep technical, this JEDEC training is a great resource. Wonderful.
And for our listeners, we'll make sure to put all those links below so you can dig in. And if you want to get your feet wet in DDR5, I think we'll give you more than maybe you want all at once, but we'll give you all those resources. Gentlemen, thank you so much for all your insight and breadth. One thing I keep forgetting to ask you, Randy, is when is that DDR5 standard coming out? Isn't it coming out soon?
Yeah, it is. The last release was October, November 2021. This was added a lot of new features. There's a lot of activity in JEDEC now to move to higher speeds. And so, this is in the final stages of approval within JEDEC. Of course, we can't share the exact date, but this is definitely imminent. And so if you're a designer thinking about higher speeds in your roadmap, going to 6400 and beyond, be prepared for this new version of the DDR5 spec that's imminent.
Okay, well, thank you for this session of drinking from the fire hose. It's been really fun for me. I hope you guys have enjoyed it, and I'm positive our listeners will. Thank you both for joining me today and sharing your knowledge.
Thanks, Judy.
Thank you.
To our listeners, thanks so much for joining this conversation with Randy White and Stephen Slater of Keysight Technologies. Again, go dig into those show notes. We've given you lots of good resources to dig in there, and make sure you go sign up for their webinar where they'll talk about this more in depth. And that's September 13th. I think it'll come out about a week after we publish this podcast. So that is also in the show notes below. Thank you so much for being with us today on the Ecosystem Podcast. We'll see you next week. Until then, remember to always stay plugged in to the ecosystem.